Other questions? Okay, so in the last few lectures we were discussing about this geometrical phase. Just to give a short summary of what this Baire phase or the geometrical phase is, what we were assuming is that the Hamiltonian now depends on certain parameters, like the width of a potential well or the height of a potential well, etc. And these parameters might be changing in time. If those parameters, they are time dependent. Now, if they change in time, we had seen that the state, if it always stays in the nth state. Now, of course, it is time dependent. If you start with an nth state, it stays in the nth state of the current Hamiltonian, within its current values of the parameters. Now, of course, this doesn't mean that the wave function doesn't change at all. The wave function, in fact, changes. I mean, now we have a wave function with the new parameters, but there is also a phase that the wave function gains due to this very small change of this parameter. And that phase is what we call the geometric phase. And in the Tuesday, the Baire phase is defined as, let's assume that the parameters, they start with certain values, and after some time t, you get exactly the same values of the parameters. So you make kind of at the t equal to 0, you have a Hamiltonian. At the final time, capital T, you also have exactly the same Hamiltonian. Now, during this process, the wave function x at the time t is in fact psi n x at the time 0. Due to the energy, there's a time dependence. There's a phase, minus I over h bar En of t prime dt prime from 0 to t. This is called the dynamical phase. And then we have this additional phase, which we call the gamma n, let's say, t. This is what we call the Baire phase. And we had seen that the Baire phase, we can write it as I times the integral of psi n gradient with respect to our parameters, psi n d lambda. And in fact, for any time t, we can just say that this is, you start from lambda 0 up to lambda t. And then the Baire phase, this gamma n of t is nothing but I over 1 period, because we start from some values of our parameters and we end up having the same values, psi n d lambda. And we had also seen that this is actually a real number, because that matrix element, whatever our wave function, is either 0 or pure imaginary. When we multiply it with I, it becomes a real number. So this is actually a phase. Now, furthermore, we can also write this as I, the curl with respect to these parameters, lambda, of this matrix element, integrated over the area enclosed by, I mean, we are just kind of imagining a parameter space, and the lambdas, they just go around a closed path in this parameter space. This gradient is in that space, and this curl is also in that space. Or either we can write it as a line integral in this parameter space, or as a surface integral in the same parameter space. So also it's evident in this final expression that if you have a single parameter, you cannot really have a Baire phase. And basically, we have two different ways of evaluating the Baire phase. So one is actually calculating the wave function itself and see how it evolves in time, and just determine this phase from the time evolution of the wave function. Or we can just use this expression. They are the same thing. The nice thing about this expression is that you don't need to know the time dependence. You only need to know the wave functions as a function of the parameters that are allowed to change. You don't even need to know how the parameters change. So you see, there's no time dependence over here. The wave functions, you should write it in terms of the parameters, and then everything can be evaluated. There's no need for time dependence. Now let's see how we can calculate the Baire phase for a given problem. If you remember, we had already studied the problem of a spin in a magnetic field. So we had this z-axis, and there was this magnetic field vector which made an angle alpha with the z-axis, and it just traced a cone. So it formed such a cone, and there was its angular frequency was given by omega. Now this problem, we already had the explicit solution, explicit time-dependent solution, and this was one of the examples which we studied to see whether the adiabatic theorem works or not. And we actually saw that if you start from a state that is in the direction of the magnetic field, it always stays in that state. The probability of making a transition just goes to zero in the adiabatic limit, which we had defined as omega over omega 1 goes to zero. Now this omega 1, we had the energy values, they were h bar omega 1 over 2. This omega 1 is the energy. In a sense, omega 1 measures how fast my wave function oscillates, and omega measures how fast my magnetic field changes. So as long as the magnetic field doesn't change in a couple of oscillations of my wave function, we have the adiabatic limit. Now let me just take the wave function at the time t in the adiabatic approximation. Let me just write it straight away. E to power I omega 1 t over 2 e to power I omega cosine alpha t over 2 e to power minus I omega t over 2 xi plus at t plus I sine alpha sine omega 1 t over 2 e to power minus I omega t over 2 xi minus of t. So this is the approximate solution close to the adiabatic limit. Now we see that this is the transition amplitude. So we started with a chi plus state at t equal to 0, and the second line is basically describes the transitions to xi minus. And the adiabatic limit in the adiabatic theorem tells us that in the adiabatic limit, these transitions are not allowed. They will not happen. And if you look at over here, the adiabatic limit is the limit that omega over omega 1 is just negligible. So if you neglect that term, then there's no transition consistent with the adiabatic limit. Now if you look at the first term, so we started with xi plus, and ignoring the second term, the exact adiabatic limit, the first term is the initial state, basically. Well, there is this dynamical phase, which is nothing but E over h bar times t. Energy is h bar omega 1 over 2. So this is the dynamical phase. What remains is our adiabatic phase, geometrical phase. These two terms is our geometrical phase. So directly looking at the time-dependent solution, we can actually calculate the geometrical phase. And so the phase over there is nothing but cosine alpha minus 1 times omega t over 2. This is gamma n of at time t. Now the Berry phase we defined as the phase that it acquires from the parameters start from one value, they change in time, and then you come back to your initial Hamiltonian. Now the one full circle, or the period of this rotation of the magnetic field is nothing but 2 pi over omega. So after 2 pi over omega, we have the initial Hamiltonian that we started with. So gamma n of t is equal to cosine alpha minus 1 omega over 2 times 2 pi over omega. So this is our Berry phase. Now, if you remember our first example of the Baire phase, we said that the Baire phase, if you remember, we had this basketball, and the Baire phase was related with the, if we take a pendulum, we moved it around the basketball, and it depended on the solid angle that was covered by the circle that we made. So let's see if we can find a similar relation over here. So this is my magnetic field. Let's say this is B, it is constant. This is actually a part of a sphere. Now, what is the area of this sphere? What is the area of this region? Well, it's the solid angle. That's what I'm trying. I want to write in terms of this alpha. I know this alpha. So in terms of alpha, what is the solid angle?
So that side is sine alpha 2 pi 1 minus cosine alpha times pi.
So you're trying to cheat? Let's evaluate integral. D omega. This is equal to, well, of course, the area will be just b squared times d omega, or b squared d phi. Phi goes from 0 to 2 pi, and d theta, sine theta, and theta goes from 0 to alpha. So this is 2 pi b squared times minus cosine alpha plus 1. Or the solid angle covered by this rotating magnetic field will be just, if we divide by b squared, it is 2 pi times 1 minus cosine alpha. And gamma n of t is just minus omega over 2. In this form is a simple expression. Well, we can do better than this. I mean, here we had a specific problem, and the magnetic field was making some simple motion, so we could actually calculate this Baire phase. But we can just, for arbitrary motion of the magnetic field, as long as it satisfies the adiabatic condition, we can still calculate the Baire phase. So let's start with psi n, or psi plus. Now the psi plus, that is the state whose spin is in the direction of the magnetic field. We can write it as cosine theta over 2 e to power I phi times sine theta over 2 at a given time. Now theta is in fact alpha. In our previous problem. So if we only have, let's say, the magnetic field going around the z-axis, so theta would be just alpha. But I mean, this approach we can use for any variation of the magnetic field in time. And we will only assume that the magnetic field, the magnitude is constant, it is slowly changing its direction. So what we need to calculate is psi plus, gradient psi plus. Now we have two parameters. We can just treat this as the component. As our parameters, we can treat the components of the magnetic field as our parameters. And we can also write this gradient operator in spherical coordinates. And in spherical coordinates, this gradient of psi plus would just be, okay, well, let me write it in general, psi plus by dr, r hat plus 1 over r psi plus by d theta, theta hat plus 1 over r sine theta, psi plus by d phi, phi hat. Of course, r is actually the magnitude of the magnetic field, which is constant, so the first term doesn't really appear. Now, if you calculate this, now I will just skip the steps. This is just 1 over r sine theta, d by d theta, sine theta of I sine squared theta over 2 divided by r sine theta in the r hat direction. And this is from the sorry, I wrote the wrong thing. This is the curl. This is from the curl. This is from the gradient. Now this part, well, you can just look up in the book also. This is the gradient, matrix element of the gradient. Here, the remaining is the definition of the curve. And you can just simplify this, and this just becomes I over 2r squared r hat. Now, the nice thing is we know that the gamma n is I times the curl of the matrix element of the gradient with respect to my parameters integrated over the area. This is equal to minus 1 over 2. Well, this integral is nothing but 1 over r squared. This curl is 1 over r squared in the r hat direction. Dot dA. But this combination is nothing but the solid angle. Differential solid angle. So we have the area, we take the component that is perpendicular to the radius vector and divide by the r squared. That's the definition of the solid angle. So are you familiar with solid angles? So let's just vary over the radius squared. And so we obtain our result, minus gamma over 2. At least in the previous special case when we had this magnetic field doing uniform circular motion around the z-axis, we had seen that this was correct, and now we have, in fact, whatever the magnetic field is doing, it can be doing in a kind of weird motion around any axis, not necessarily around the given axis, but this will still be true. The bare phase is nothing but the solid angle covered by the closed loop that the tip of the magnetic field traces, divided by minus 2. Let's make another application of this thing. Now it will be the Aharonov-Bohm effect. Well, initially it was not proposed as a bare phase, but then it was later on discovered that this was actually a special case of a particular case of a bare phase. So let's first discuss what this Aharonov-Bohm effect is. So what we'll assume that there is a region of space, which can be a solenoid, where the magnetic field is non-zero. Out of this region of space, the magnetic field is 0. Exactly 0. That is what we will assume. And as a concrete example, let's just assume we have a solenoid with inside B non-zero, outside the magnetic field is 0. And let us also assume we have a particle, a charged particle, that is confined on a ring of radius, let's say B, around this solenoid. The magnetic field is just constant, but non-zero inside the solenoid. Outside there is no magnetic field. So one would naively at first sight expect that the electron on this ring shouldn't feel the magnetic field. So it is always in regions which are non-zero magnetic field. But nevertheless, although there is no magnetic field, there is a vector potential. Outside, the vector potential is non-zero. It's just the curl is 0. So let's first study what's the Hamiltonian of a charged particle in an electromagnetic field. Do you remember? We have a charged particle in an electromagnetic field described by vector potential A and scalar potential phi. How can we write down the Schrödinger equation?
Kinetic term plus phi.
And what's the kinetic term? 1 over 2m. Hamiltonian is not equal to 1 over 2m minus h bar squared Laplacian plus q phi. This is not our Hamiltonian in an electromagnetic field, but our Hamiltonian would be 1 over 2m minus I h bar, the gradient, minus or plus minus qa squared plus q phi.
Did we do this?
No, you,
Okay.
you have probably done it in 431 or in
No.
311, classical mechanics.
Makes sense, but I don't remember.
Now, let's see. There's essentially one important property that the electromagnetic fields and the Schrödinger and our description of nature should satisfy. It should be gauge invariant. So in electromagnetism, you have probably seen the gauge invariance. So if you have, for a given electric and magnetic fields, you can always write these in terms of the vector and the scalar potential. The electric field will be minus the gradient of phi minus dA by dt, and the magnetic field you can always write as the curl of A. These are the definition of the vector and the scalar potentials. Now these potentials have an interesting property. If you just change A to A prime, which is A plus the gradient of some function, which can depend on the position or even time. And if you change phi to phi prime, which is phi minus del lambda over del t, then the electric and electric field does not change. And similarly, the magnetic field does not change. Well, the magnetic field is kind of trivial to see. If you just take the curl of the gradient, it is 0. So there's no contribution from the lambda term. For the electric field, the contribution to the first term, the gradient of phi, and the contribution to the second term, the time derivative of the vector potential, they just cancel each other. Well, of course, now there's a problem. If the vector potential and the scalar potential, we can just choose them arbitrarily. In a sense, we have this arbitrariness in the choice of the vector and scalar potentials. Which one should we use? In principle, all of them should give me the more or less the same physics. Maybe not exactly the same wave function, but the physics should be the same. So let's try this one.
So the square of the amplitudes will be same.
Hmm?
Probability amplitudes, square.
The probability amplitudes should be the same, the energies should be the same. Let's also see one more thing. Now we always say that, okay, the phase of the wave function is not physical, so we can just define the phase as we wish. But the phases that we consider were, most of the time at least, they were just constants. Now let's see what happens if we have a time-dependent phase. So let's say psi, instead of the wave function, let's say let's consider the wave function psi prime, which is equal to e to power I, some lambda, which can depend on position and even time, psi. And let's also assume that h is a function of a and phi acting on this psi is equal to e, or not e, I h bar d psi by dt. So psi satisfies this equation, where h is given by this expression over here, the Hamiltonian. So this tells me that I can write psi in terms as e to the power minus I lambda psi prime, and let's just put it over here in the Hamiltonian. Now the thing is, let's start with minus I h bar gradient acting on psi. Now the gradient will act also on lambda. This is minus h bar, the gradient of lambda, psi prime, plus e to the power minus I lambda, no, let me erase this one, times gradient of psi prime, everything multiplied by e to the power minus I lambda. So in a sense, the minus I h bar, now here I have the minus I h bar, minus I h bar operator just becomes minus I lambda times minus I h bar, the gradient, minus h bar times the gradient of lambda. So the gradient operator just becomes this new operator when we just commute it over e to the power minus I lambda. 1 over 2m minus I h bar Laplacian minus q over m a squared acting on psi. This just becomes e to the power minus I lambda 1 over 2m minus I h bar gradient minus h bar gradient of lambda minus q over m a squared psi. So if we define minus q over m a prime as minus q over m a minus h bar gradient of lambda, so the new Hamiltonian h is a function of a and phi. In a sense, it just becomes acting on psi is in fact e to the power minus I lambda h. Let's see, this is a plus. Now let's see, this is q. No, there's no m, by the way. There's no m over here. Plus h bar over q, gradient of lambda, phi acting on psi prime. So the effect of this multiplying by the phase is, in a sense, just changing a with the gradient of a function. Well, this looks like a gauge transformation. And in a moment, it will look even more like the gauge transformation, because if you remember, the gauge transformation also involved the change of phi. But up to this point, it's only the a that we have modified. But let's look at the time dependence. We have the I h bar del psi by dt, because the h acting on psi is equal to I h bar del psi by dt. And this is equal to I h bar, the time derivative of e to the power minus I lambda psi prime, which is equal to I h bar times minus I del lambda by del t times psi prime plus e to the power minus I lambda del psi prime by del t. And this is equal to h bar del lambda by del t psi prime. Now this is a common factor. e to power minus I lambda plus I h bar del psi prime by del t e to power minus I lambda. Now let's put everything together. We had already seen that, okay, this is our A prime, e to power minus I lambda, h with parameters A prime and phi acting on psi prime. This is equal to I h bar del psi prime by del t multiplied by e to power minus I lambda plus h bar del lambda by del t psi prime multiplied by e to power minus I lambda. Okay, these exponents are the same everywhere, so I can just cancel them. So we have h A prime phi minus h bar del lambda by del t times psi prime is equal to I h bar del psi prime by del t. But this thing over here is nothing but h A prime phi prime, where phi prime is now equal to phi minus h bar over q del lambda by del t. Remember, h has various terms plus q phi. So if I just change the definition of phi and absorb this factor in the definition of phi, I can just write the whole thing as a single Hamiltonian with a different phi. Now let's also look A prime. This is my A prime. But this is nothing but a gauge transformation. So psi and psi prime satisfy the same equation, and the only difference is that there's a gauge transformation between the vector and scalar potentials. So basically they describe the same physics. Even though the wave function can be position and time dependent, the phase can be position and time dependent, the difference is just a phase transformation. It's just a gauge transformation, which just doesn't change anything. Now let's see what this means in our case. Well, for the time being, let's just keep this in mind. That I can just multiply my wave function with a phase, position and time dependent phase, and then the new wave function will still satisfy the same Schrödinger equation, provided that we consider a gauge transformation of the vector and scalar potentials. Now let's come back to this example first. Now the wave function that the state will the wave function will only depend on phi. It won't depend on anything. So because that is this is here where we have the magnetic field. Here is our ring. Our particle is confined on this ring. So we can just say, let's say x-axis, the y-axis, the position at that point. This is the angle phi. Now the vector potential for this case, this is just the flux divided by 2 pi r in the phi hat direction, provided r is larger than a being the radius of the solenoid, 2a. So out of the solenoid, this is our the vector potential. The scalar potential is 0. We have already fixed one gauge. We fix this gauge because for a given magnetic field there are infinitely many possible vector potentials. But we just fix one gauge, and in this gauge, this is what our vector potential is. And the curl of that vector potential, it is a magnetic field, which is 0 for R larger than A. So it just describes, in a sense, it describes what's called a pure gauge. It doesn't correspond to a magnetic, it corresponds to 0 magnetic field. And also this phi is just B times pi A squared, is the total flux, magnetic flux through the solenoid. Now let's write the Hamiltonian. 1 over 2m minus I h bar gradient plus I h bar minus I h bar gradient minus q times A squared. This is our Hamiltonian, there is no phi. This is equal to 1 over 2m minus h bar squared times the Laplacian minus I h bar plus I h bar q twice A times the gradient. Well, A and gradient, they don't commute because they are position dependent, but due to our choice of gauge, the commutator just depends on the gradient of A, which is 0. Plus q squared times A squared, and A squared is just phi squared over 2 pi B squared. We are on the ring, so that's why we don't have an R. R is equal to B. A is, in a sense, constant in the phi hat direction. Its magnitude is constant on my ring. Now you can just write the Laplacian, fixing R is equal to B, and you just obtain this is equal to 1 over 2m minus h bar squared over B squared, D squared by D phi squared plus Q phi, no. What is our A? 2 pi squared. Q phi over 2 pi B, all of this squared, plus I h bar Q phi over pi B squared D by D phi. Well, this is a second order differential equation with constant coefficients. The solution has to be in the form e to the power I lambda phi, the general solution. And you can just substitute it over here, solve for lambda, and you get lambda is equal to beta plus minus square root of beta squared plus epsilon, where beta is q phi over 2 pi h bar, epsilon is 2mb squared e over h bar squared minus beta, etc. Now there is one condition though. I mean, phi is not unique. At a given point, phi can have, let's say, 0, 2 pi, 4 pi, they all correspond to the same point, but the wave function should have a unique value at a given point. So that basically tells me that lambda should be an integer. But you see, lambda, the value of lambda depends on energy. But the energy, that basically means energy can only take discrete values, and the energy eigenvalues turn out to be h bar squared over 2mb squared n minus q phi over 2 pi h bar squared, n is equal to 0, plus minus 1, etc. So the long story short, here we have a simple system which we can exactly solve, in which the electron, the charged particle, never enters the region which has a magnetic field, but nevertheless the energy values do depend on the magnetic field, because in a sense it feels the vector potential. But you see, vector potential itself is not really it is physical in the sense that it does have consequences on the motion of this charged particle, but it's not in itself measurable. Only the electric and magnetic fields are. But you see, the result only depends on the magnetic field. It only depends on phi, which is the total flux. So again, the result is still gauge invariant, although the result is the energy level depend on the vector potential being non-zero. So in a sense, the electron even feels the magnetic field that it never felt. It feels it, which doesn't exist. Yeah, exists, but in a faraway region. Now, the actually measured dependence on this magnetic field was, we have this in the double slit experiment. Now, in the double slit experiment, what was done is that you put some magnetic field in this region. There is a source, you send your particles, and here is the screen. So you basically send the electron, you do the electron interference. And the interference pattern that you observe over here will depend on the magnetic field in this region. Well, you can just put these rings at a faraway point, these dots at a faraway point, just to make sure that they are far from the magnetic field. Now, this we will discuss in the next hour. Any questions on the previous things?
Ben hala matematik dışında çok ikna olmadım şey. Yani yok, yok ama bazen şeyler değişiyor.
Well, of course, I mean, okay, on one hand, here we have the hypothesis, the theory, let's say, that says that if there is a magnetic field in a region, the electrons, the charged particles, would feel this magnetic field even if they don't enter the region which has a non-zero magnetic field. So this is what this claim is. The final conclusion should be based on experiments. And we have experiments which actually show this. Now, basically, the question is, how physical is the vector potential? We always say that, okay, electric and magnetic fields are the real physical things. They have the physical consequences. But basically, this tells us the vector potential itself has physical consequences.
Oh, right. As you said at first, I mean, thinking about the wave function, some part of wave function enters.
Well, in this example, which is probably the reason that the book discusses, you assume that the wave function there's such a potential that there's a Dirac delta potential, which doesn't allow the wave function to spread out of this ring.
Or into
Psi r is proportional to e to power lambda phi I lambda phi times Dirac delta r minus b. This is your wave function. So there's no just leaking into the region where there is the magnetic field.
normal speed.
Hmm?
Okay.
And this is the actual, well, there's a reference in your book to the actual experiment that was done using this setup, more or less. Well, of course, in this setup, you can still claim that maybe the tail is just goes into the region where you have a non-zero magnetic field. But then if you claim, if your hypothesis is that, then you should actually prove that that tail gives rise to the observed phase difference.
Can you just go over it? So it just, the energy levels depends on just like the flux, right?
Yes. So although the vector potential itself has physical consequences, we still have gauge invariance.
So what, I mean, if they depend on flux, like how it doesn't, okay, there's B squared.
No, there's no b squared. Where?
H bar squared over 2 and B squared.
This one.
I mean, small b squared, okay, I told.
No, small b is the radius.
Just depends on like size of the magnet.
Well, you see, if in the limit that you take b to infinity, it should just be one-dimensional motion on a straight line. So you have continuous energy levels, and that's basically what this 1 over b squared does. The spacing between various levels goes as 1 over b squared, and in the limit as b goes to infinity, you have a continuum.
Hocam diyorsunuz ki başka bir yerde olmaya kadar bize bitiriyor.
Yes, it seems to be so, at least, both theoretically and experimentally. It influences us through the vector potential. So it just seems that the vector potential has a real physical existence in a sense. So it's the vector potential that is influencing us.
Like, could it be the case if there is no magnetic field but electric field in a confined region? If you could build something like this setup, like is it something to do with like E field is not conservative or something?
Conservative? What do you mean non-conservative?
I mean, like I don't know. In classical case, it depends on the velocity. Like, it depends on path, not just position.
Mm-hmm. Now we will see how this changes. We will be generalizing this concept in the Hour1 case, and that we can also apply to what you claim.
It's great.
It's a break time now.